Yeah, the question says determine the approximate area on the curves of the following graphs, then interpret your answer. That's number 1A. Okay, so in order to do that, we've got to count basically the number of rectangles, the area of each rectangle, and use the y variable and x variable to interpret the meaning of the answer that we get. Okay, the y variable is velocity and the x variable is time. So we'll be doing that with an example. Now, question number 2. Well, just to recall, just remember that anytime you see you look at a graph, the line or the curve that you see shows you the behavior of the y variable. So this line is going from up to down, is going down because the x variable always increases from left to right. So the mere fact that this line is going down, it means that velocity is decreasing. Always associate the line with the y variable. Okay. That's number 1A. Number 2A, it says determine the gradient of the following graphs, then interpret your answer. So we have to apply the gradient of this line. This line is indicating that distance is decreasing. Distance from a reference point, for if you want to put it that way. Time is always increasing from left to right. Okay, so please bear that in mind. So we're going to use some example, 2 examples for this, one for the area, one for the gradient. For the area, we have a curve, and there's a shaded region from -1 to 4. And the curve that we see shows you the behavior of the velocity, which is the y variable. So according to this line, the velocity is increasing to a maximum and decreased to 0, as time always increases from left to right. Although the x variable always increases from left to right, but the y variable, which is velocity in that case, as the line depicts, increases, reaches a max, and decreases to 0 meters per second. So we have to find the area. And by doing that, we can find an approximate area by counting the area of each square. So let us zoom in on this just to get a little bit more visibility to approximate the area by counting the squares, which is squares that are shaded. So each one will give it a unit square area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then you have 17.5, and then 17.5, and this could give us 18, and this one can give us 19. Little extra we added to the 17.5 we had gotten. So that would be 19 units squared. Okay, 19 units squared approximately. So the area under this curve from -1 to 4 is equal to 19 units squared. Now we have to recall that velocity is equal to distance over time, the change of distance over the change of time. So if we make distance the subject of the formula, the area, which is the product of length times width, okay, the width will be time and the length will be velocity. When you multiply velocity by time, you get in distance. So therefore that 19 units squared can be interpreted as 19 meters. Agreed? So that's the interpretation of this area under this curve, a velocity times curve. The area beneath a velocity times curve will give you distance. Okay? Yes. So now we are moving on to the second problem, which asks us to calculate the gradient. So here we have an example, the gradient of a line. This line that you see shows you the behavior of distance. Distance is decreasing from, from a reference point, yes? Now, gradient is equal to the change of y over the change of x, y2 minus y1 over x2 minus x1. Now, change now, which is a difference, can be denoted with that symbol called delta. Delta is the D sound in Greek. That's a letter for the D sound in Greek. In English, the D sound is a D. But since D was already used for distance, so the mathematicians went to the Greek alphabet and to select that symbol called delta. Here it is. We can just check it out in the Greek alphabet. It's very interesting when the mathematicians converting, or the physicists also converting symbols to words to symbols. If the English alphabet does not suffice, you normally go to the Greek alphabet. So the delta is the symbol for the diphthong in Greek, and D is our D in English. D is already used for distance, so they went to the Greek symbol for the diphthong, and now capital delta, small delta. Small delta is also used also for small difference, yes, and capital delta for difference generally. Okay, so if you see small delta anywhere, just know it denotes a difference, okay, in physics, which is a subtraction. So delta y over delta x will give us the gradient. Here it is, delta y over delta x, y2 minus y1 over x2 minus x1. So what we need 2 points in order for us to calculate the gradient. So we can look for 2 easy points, 0, 80, 0 on the x, 80 on the y. That could be the first point. So pair of coordinates, 0, 80. And the next easy point could be 40 on the x and negative 20 on the y. 40, negative 20. Okay, so y2 minus y1, that would be negative 20. Subtract 80, it is y1, and x2 is 40. Subtract x1, which is 0. Okay, negative 20 minus negative 80, that will give us negative 100. Okay, divided by 40. 40 minus 0 is 40, and 40 into negative 100, that should give us negative 2.5. Okay, now recall that distance over time is velocity, right? Because remember, the y-axis here is velocity, distance, and the x-axis is time. So when you divide 80 minus 0, you are actually dividing a distance divided of 40. 80 minus, right? Now minus 20 minus 80, that would be a distance, okay? And 40 minus 0, that would be a time. Distance over time is velocity. So that is actually negative 2.5 meters per second. So this will be the interpretation of the gradient here, which is velocity, okay? And the interpretation of the velocity times graph, the product thereof, will give us distance, okay? So please apply that to the 2 question number 1 and 2 in the assignment. Yes? Yes.